What's going on? It's me, Jordan. And before we get to this episode of Below the Scope, I want to remind you to please leave a comment, or even ask us a question in your favorite podcast app. And then subscribe so you can be notified whenever a new episode drops. And please tell a friend when it does. We appreciate it, and it helps us grow the show. Thanks, and here we go. I'm Jordan Chapman, and you're listening to Below the Scope from B-SCI. Our society runs on fossil fuels, which are also called hydrocarbons. And even though they cause problems like increased greenhouse gas emissions, air pollution, ocean acidification, habitat destruction, our society is still pretty dependent on them. So what if there was a place drowning in hydrocarbons? A moon full of hydrocarbons. A place where they rain from the skies, flow like rivers, and pool into lakes.
The crew of Artemis 2 now bound for the moon. Humanity's next great voyage
begins. Not that
begins.
moon, but Titan, one of Saturn's moons. A place we'll be looking at below the scope.
When I was little and the Voyagers flew by the giant planets, it was very formative for me. And so I got a passion for studying planets pretty early on. And right as I was finishing my graduate work, which was in exoplanets, the Cassini mission had arrived at Saturn. And so I joined them as a postdoc and started my research at Titan at that point.
This is Dr. Jason Barnes.
I'm a professor of physics at the University of Idaho and the deputy principal investigator of the Dragonfly mission.
Born Dragonfly later.
Yeah. So, the Voyager 2, for instance, flew by Jupiter, and it was moving really fast and didn't slow down. And then it flew by Saturn, and flew by Uranus, and flew by Neptune. Cassini, on the other hand, was designed as sort of a follow-up. So it got to Saturn, and then it fired a rocket and slowed down. So it remained in orbit around Saturn for 13 or 14 years. And so it was able to do a much more thorough and in-depth study of the gas giant planet itself, but also all the moons and the rings and everything in the sort of Saturn environment.
Okay, so is that when we started to see evidence of these hydrocarbons started in the atmosphere, or did we kind of, or was there any point before that happened where we kind of speculated that might be the case?
Well, the first indication that something interesting was happening was in 1948 when Gerard Kuiper from Arizona looked at Titan with a telescope and looked at the spectroscopy and showed absorption due to methane in the atmosphere. So, right, methane is like natural gas, CH4. And so that's sort of a hydrocarbon. That was the first indication that both Titan had an atmosphere, but also that it had some hydrocarbons in it. But it was really the Voyager flyby that confirmed the existence of particular higher order hydrocarbons. And then Cassini was able to follow that up and find even larger, more complex hydrocarbons in his outer atmosphere.
My name is Ashley Walker. I am the founder and president of Black and Astro, and I am a final year PhD student at Howard University.
Black and Astro is a nonprofit that celebrates and amplifies the voices of Black scientists and engineers in the space community. And Ashley used to do research on Titan.
So my research on Titan, when I did work on Titan, I did two things. So I looked at its prebiotic chemistry.
That means understanding how early Earth's chemistry might be similar to Titan's.
I also looked at its upper cloud layers and its upper atmosphere.
I am wondering how those hydrocarbons got there. How the entire moon become full of hydrocarbons?
They're coming through photochemical haze, and they're also coming through the formation of UV. So, for example, it's clear and sunny, right? And you have it hitting on energetic particles. It then creates and form other photochemistry.
So at Titan, there in the outer solar system, it has a methane-dominated atmosphere, as early Earth may have had. And it's solar ultraviolet that busts up the methane, pulls the hydrogens off the methane, and those ultimately combine then with each other to make larger and larger hydrocarbon-based molecules in the upper atmosphere of Titan that slowly raid down onto the surface over the course of decades and coat the surface in this sort of organic gunk.
But these can also be liquids.
It has methane and ethane lakes and rivers.
Which kind of sounds like a water cycle.
Essentially. Essentially, they have a methane cycle and a methane and ethane cycle.
And this makes Titan sound sort of similar to Earth.
Well, there's two ways primarily. One is chemically and one is geologically. So the chemistry is sort of this nitrogen-based atmosphere, which 95% of Titan's atmosphere is nitrogen, same as ours. But with this methane that's able to produce that additional hydrocarbon and its ability to mix with potentially liquid water. Of course, the temperature is very cold, but that kind of water with methane and organic chemistry is something we think may have been true on early Earth. We don't know, but we suspect that those conditions may resemble what was happening on early Earth. But the fact that there's rainfall means that the surface geology on Titan is really dominated by rain and rain erosion in a way that only Earth among the solar system planets are. So we see these little channels and canyons and river valleys, and those river valleys empty, into alluvial plains and basins in a much way, that is very familiar to us here on Earth.
Even the dunes on Titan are like the ones we see here on Earth, but with a bit of a twist.
Right, on Earth, you take the Earth's bedrock and you break it down into tiny particles. That's what makes the dunes. Instead, it seems like the sand dunes on Titan are coming from the organics. So that stuff is coming out of the atmosphere. It plates onto the surface. Somehow it's building into these sand-sized particles that then blow around, and such that about 15 to 20% of Titan's total area is covered in sand dunes. And they're the same type of sand dunes we see mostly on Earth, which are longitudinal dunes. We don't get any of these in the Western Hemisphere, but you see them in the Saharan Desert, in the Arabian Desert, in the Taklamakan Desert in China, the Namib Desert in Southwest Africa. And these are like 100-meter high, maybe a kilometer-wide dunes that extend for like tens to hundreds of kilometers in the downstream direction anyway. But the particles aren't made of, SiO2. They aren't made of, rock the way they are on Earth. They seem to be made of these solid organics. So think giant 100-meter high mountains of coffee grounds.
So an entire moon full of hydrocarbons right in the middle of our solar system. So I guess a question that I've been having is that if there's like these big reservoirs of hydrocarbons on Titan, have people been talking about mining Titan for these hydrocarbons? Or is that like, I know it's, who knows how long away? Would it be feasible? Has that been something that's been talked about? Is this something that's even recommended? What's the ethics behind that? Can you talk about that for a little bit?
I haven't heard anything about mining just yet. It could be under the radar and I just haven't paid attention to it. I would not suggest mining on Titan. Just like it's giving like how the Ocean Gate guy wanted to go to the edge of Venus.
That's Guillermo Zonline, who founded Humans to Venus, a nonprofit that wants to make Venus a long-term destination for humanity, and also co-founded Ocean Gate, but left in 2013 with a minority stake.
And I'm just like, well, by all means, go ahead, but I would not suggest it.
I also asked another member of the Black and Astro community.
Yeah, so my name is Andrea Bryant, or I guess Dr. Andrea Bryant. I am a Provost STEM Fellow at Brown University in Providence, Rhode Island.
She's a planetary seismologist and has also been doing research on Titan.
I don't think so. I mean, you know what? It's probably possible, but we'd have to put a lot of research into that. The issue is just trying to create Titan environments so its gravity is 1/7 Earth's gravity, and then the atmosphere is 1.5 the atmosphere of Earth. And so when you have those ingredients, and you try to replicate that on Earth, well, it can be very dangerous. So it's just, I'm thinking, trying to take things that are under Titan conditions and then bring it back to Earth conditions. Well, first you have the expansion of the methane from liquid to the gas. It almost would most certainly cause things to explode. And then to keep things that cold, 94 Kelvin, and transport it here, and then keep it under enough pressure that it's actually going to stay liquid as a power source. Maybe if we kept it in space, and we were creating power in space, maybe somebody listening will one day create some amazing, power system. But you probably have to have your space system out in space, keep it there, and then somehow transport the energy from a space energy factory to the surface of Earth. Or maybe you're just trying to power the moon, or, you know. But also, another thing is that it takes 6 years currently to get to Titan. So, you know, you'd have to have a lot of money.
So I do have a stupid question, and you don't have to answer if you're like, that's too stupid. Okay. But so one thing, you know, as you learn about Titan, you're like, oh, it has hydrocarbons on it, and then you realize that Earth is full of hydrocarbons, including the ones that like power like our cars and things like that. Would it be feasible, or and then a follow-up question is, would it be recommended that one day, far from the future, would we bring those hydrocarbons back to Earth?
There are these hydrocarbons on Titan, and we, you know, the natural gas industry here on Earth is a very prolific one, and we drill for both gasoline but also you know, natural gas, and pump it around the world and put it on these giant ships and float it across the ocean to be able to burn it and use it for fuel. You could totally do that. It is about the most expensive way I can imagine to bring in power. Flying things through space is pretty hard in comparison, and so I think importing all those to Earth, in addition to causing changes to our atmosphere that we may not like, probably would not even be an economically feasible mechanism, which is almost unfortunate, because like if we had Exxon funding, we'd get a lot more done than we do from public space science funding.
So we're probably not going to power our society using Titan fuel. But what if Titan could tell us something else? Like, as a geologist, I guess, and one who studies soils, I can sort of think about the ways in hydrocarbons formed here on Earth, even in Earth's early atmosphere. But I've been having a tougher time thinking about how that happened on Titan, and then like how that led to like Titan's like almost like water cycle of like hydrocarbons. So Ada, could you walk me through that?
Yeah. So yeah, on Earth, of course, all the hydrocarbons are ultimately produced by life, right? This planet is infested with life everywhere, and so there's carbon molecules almost all over the place, in the soil, on rocks, in the bottom of the ocean, and it's all ultimately derived from biology.
With Titan, it's very similar to early Earth, and that's why we're studying it, because it can give us hints and clues of what was happening back then. So you want to think of this as like forensic science, where you're studying a crime scene and you're trying to piece together like a whodunit situation.
So we know that hydrocarbons that power our society were formed a few 100 million years ago. Coal and oil form in environments that are like pressure cookers on the time scale of millennia, just in different places. Coal forms in wetlands when dirt organic matter, especially plants and trees, falls in a swamp or marsh and gets buried by dirt and sediment that continuously piles up on top, increasing the heat and pressure. Oil is similar, but this happens in the ocean, and because the organic matter in the ocean is mostly algae and plankton, that organic matter isn't as tough and as hardy as plants on land. So they form more of an ooze that becomes liquefied under the heat and pressure. And in both situations, natural gases can form, like methane and ethane, as that organic matter decays. But the crime scenes Ashley is talking about are from billions of years ago.
So we do think about, when we think about the hydrocarbons back in the day on early Earth, when we think about all the experiments that the Miller-Urey experiment, for example, have done, we want to think about how that was also replicated to help us understand early Earth and how the hydrocarbons and how everything was formed back then.
In 1952, at the University of Chicago, Stanley Miller, under the supervision of Harold Urey, performed an experiment with water vapor, methane, CH4, ammonia, NH3, and hydrogen gas, H2. Miller then adds an electrical spark. The ratio of the gases in the spark were supposed to mimic Earth's early atmosphere. After the mixture was condensed and cooled, Miller discovered amino acids, the building blocks of life. The Miller-Urey experiment is our best guess of how Earth went from prebiotic life to biotic life, all the life we see before us today. But things on Earth are always moving. Wind and water break down rocks, life breaks down and erode rocks into soil, and plate tectonics basically destroys all of that. So our crime scene is trash, but we do have some evidence. Our oldest confirmed evidence of life are stromatolites. They're these rocky formations that are mats of microbial activity that build on top of each other like a weird patty. They're about 3.5 billion years old and found in Western Australia. Also in Western Australia is our oldest evidence of oil, microscopic droplets found in rocks that formed about 3.2 billion years ago. But it can be hard to find anything much more than that.
The evidence of that has been lost. It's really hard to find, get back and figure out what that chemistry might have been. So at Titan, there in the outer solar system, it has a methane-dominated atmosphere, as early Earth may have had.
And today, we announce our next mission to explore our solar system.
This is from former NASA Administrator Jim Bryant.
NASA is pushing the boundaries of human knowledge and expanding the limits of technology. Today, I am proud to announce that our next New Frontiers mission, Dragonfly, will explore Saturn's largest moon, Titan.
That announcement was from June 27th, 2019. And right now it's 2026. So we're about 2 years before Dragonfly is officially going to launch. Yeah, I mean, I think me and I'm sure a bunch of other people, when we think about like new probe landing on somewhere else in the solar system, we're probably imagining a Mars rover of some kind, like OPI or something like that. But this is, this is gonna be different.
Yeah, I mean, we were thinking about how to achieve mobility on Titan the same way we have on Mars, as you point out, with rovers, right? But we kind of wanted to land in the sand dunes, and I don't know if you've ever been off-roading in the sand.
Not off-road, but I've been to the white sands.
Okay. Yeah. Driving in sand like that, you can get your vehicle stuck real easy. And so like wheeled rovers and sand, not necessarily a great combination. In fact, those Mars rovers, initially they would drive into the sand dunes. A couple of them got stuck. I know Opportunity got stuck and had to like slowly back out over the course of a week. So they drive around those dunes now. So like maybe dunes aren't, wheeled vehicles might not be the best choice for Titan. But because Titan has air that's 4.5 times thicker than Earth's air, denser, and the gravity is 7 times lower. In fact, just having a whole rover that instead of roving around with wheels, you just slap a bunch of propellers on it and have the whole thing take off and fly actually ends up being a very efficient mode of transport. You don't have to worry about getting stuck. You don't have to worry about trafficability over big rocks or anything. You can just fly between destinations, find a safe place, put down, be able to do your science, and then fly to your next destination. So that's how we came up with the idea of just turning the whole thing into a giant, quadcopter. And eventually that became an octocopter now. So we got 8 different rotors, 2 on each of 4 stalks, and the whole vehicle masses like a metric ton. So it is big. So think of one of those big Mars rovers like Perseverance or Curiosity, except we're not quite that big. And yeah, we fly instead of drive.
Yeah, and it's I've been reading it's about the same size as like a minivan or something like that.
Not quite that big, but a Mini Cooper maybe.
Okay, a Mini Cooper. Okay, that's it. Dope. But what's the plan for Dragonfly once it reaches Titan?
Yeah, so it's mainly an astrobiology focused mission. There's a paper, Barnes et al. 2021, that for those who actually will want to go and read the paper.
This is how I actually learned about Dr. Barnes. The paper was published in the Planetary Science Journal in August of 2021. He's the first author on the paper, which means he led most of the writing. And the paper has 25 other scientists from all over the world, including the US, Europe, and Japan.
Absolutely, yeah. So, when you formulate one of these missions, you have to really think through what science you're trying to answer, what questions you're trying to answer, and then formulate your mission. Come up with a set of science instruments that you want to have, what measurements you want to make, and how those are going to inform those science requirements. So yeah, that paper is the full Dragonfly science team.
Dragonfly has 5 mission objectives.
So yeah, our first goal is that prebiotic chemistry is to figure out how far has carbon chemistry come. We're going to land in this giant impact crater that we think would have created a liquid water melt pool 100 meters deep that would have remained liquid for maybe upwards of 1,000 years. And the question is, once that liquid water mixes with the organics in the atmosphere, how far has that organic chemistry progressed toward some sort of self-replicating system? What pathways has it taken? And how complicated organic molecules is it able to construct? Our second one relates to the meteorology, sort of to figure out what role Titan's tropics play in that global methane cycle that's akin to our global water cycle here on Earth.
This means measuring things like wind speed and direction, and even trying to detect if there is subsurface methane on Titan in the same way that there's aquifers here on Earth.
Our third goal is to characterize the geology, sort of where the samples we get come from, and what rates of different processes are occurring. We're talking about wind-based erosion versus rain-based erosion or chemical erosion, transport of materials downhill and by winds and that sort of thing. Goal 4 is to try to constrain when and where liquid water may have interacted with organics, and primarily that's going to come from that deep water ocean. There may be a possibility that that liquid water ocean may ooze onto the surface in a cryovolcano, but also that organics from the surface might be able to work their way down via some process, maybe like subduction we get here on Earth, from the surface down to seed that subsurface ocean. And maybe there's life down in that subsurface deep water ocean 100 kilometers below the surface. So we're going to look for evidence of tectonism, listen for Titan quakes to see if there might be some evidence of crustal motion. And that's our goal 4. And then our goal 5 is to look for potential biochemical markers of present or past life on Titan. If there have been cryovolcanoes oozing material from the inside, and there are some sort of critters living in that interior ocean, if you sample that material that's oozed onto the surface, you might be able to find some chemical evidence that the chemistry down there is dominated, like our Earth, by biology and not by abiological processes. So those are the 5 science goals.
This is a huge project with many different scientists working on different parts of the project, like Dr. Bryant.
Yeah, so I'm a Dragonfly associate.
This means she works with other Dragonfly scientists to support the development of the mission.
I'm a theorist through and through for this mission. And I guess my PhD has been all theory. So I basically create computer toy models or simulate what Titan could look like, the inside of it. And then I add a wave field and I add like a quake, like a source. And then from the source, we can actually figure out what we're looking at. So that's what my job had been. And actually right now I'm doing a fun new project with Sam Birch, who is a river expert, like geodynamics of rivers. We're thinking about a river on the surface of Titan. And actually if you have pebbles of water at the base of that river being picked up by the flow of the river as it hits the ground or hits the base of the river, can you actually detect that with the Dragonfly seismometer? So that's what I've been thinking about.
Yeah, so our launch date is July 5, 2028 at 12:34 Eastern Time, I think it is. Like, we know, because it's like orbital mechanics, we know when the planets are going to line up. So that's our launch, the beginning of our launch period. And we can launch any time between then and I think July 26 of 2028.
If everything goes as planned, then Dragonfly would reach Titan 6 years later, sometime in 2034. And that might seem like a long time, but maybe it's just the beginning of a new era.
And I think that's really exciting. And also the tools that will help us to understand chemistry here, they're very transferable as well. Even though I'm not trying to say like someone needs to leave or anything, but understanding chemistry of microbials on Earth will help us to understand chemistry of potential microbials that could exist on Titan. Understanding the seismology of Titan will help us understand also, will help us maybe better refine some of our seismology here. Well, maybe not as much. More so, probably Earth will help us inform Titan a lot better since we have a lot more seismometers there. But yeah, I mean, it's really exciting to think about, could there be life on other planets? And this is something that when I go and volunteer, like planetariums, this is probably one of the biggest questions I get. And number one question is like, are you looking for, do aliens exist? Are we looking for aliens? Everyone wants to know about aliens. And so I think where there's no promise, no guarantee that we're going to find, Titans, like Attack on Titan, like there. Probably not, probably no aliens there. Probably not. But, we're looking for, signs of possible life like in the past or maybe little amoebas or something that could exist underneath the surface.
And maybe we go beyond Titan.
And then when I got to grad school, my current advisor, my external advisor, said, I have a project for you. And I think that you'll be great for the ice giants. And I was just like, I don't want to do that. And he was like, you're going to love it. I promise you. He was like, I think Titan is cool and we can still do some stuff for Titan. But I think everybody's all up on Titan. I think it'll be best if you do the ice giants. It'll be really great. And so lo and behold, he was right. I did actually end up really, really liking the ice giants. I like the fact that it's very mysterious and unique. There are things that we still don't know.
I asked actually how close we were to one of the ice giants getting their own Dragonfly-like mission one day.
So we initially were trying to get the flagship mission of the Uranus Orbiter probe flagship. Unfortunately, due to budget cuts, we do not.
For now? In the future? For now. Ashley said one day she would like to be a principal investigator on a planetary mission. And as far as we could tell, she'd be one of the few, if not one of the only ones to ever do that. But right now, Dragonfly and Titan are on the horizon.
This is sort of what I want to do my whole life, right? And I've been trying to get on a NASA mission, and I was on Cassini, but I was a postdoc, right? I was pretty low level. 10 years ago, my buddy Ralph and I were sketching this on the back of a napkin at the Mexican restaurant in San Antonio on the Riverwalk, okay? And now, we got the full support of the U.S. government behind us. There are a lot of amazing places to explore in the solar system, but I think, Titan's one of the most compelling. You're thinking, where can people live in the solar system? I think Mars and the Moon are good choices, but Titan is also an excellent choice. That thick atmosphere protects you from cosmic radiation and from micrometeorite bombardment. It provides the pressure you need. On Mars, you're worried if there's a hole in your dome, you're going to depressurize and your eyes will bug out like Arnold Schwarzenegger in Total Recall. But Titan has an ambient pressure that's not too different than that on Earth. It's got plenty of resources like water and nitrogen and organics. In the long term, I think Titan is one of those places that you might see people actually being able to get out to and explore, in the far future.
Thanks for listening to this episode of Below the Scope. Please tell other people about the show. It really does help. This is a podcast produced by the Black Science Coalition and Institute, or B-SCI. Thanks to our experts, Dr. Jason Barnes, Ashley Walker, and Dr. Andrea Bryant. This episode was produced, edited, fact-checked, and of course, narrated by me, Jordan Chapman. Sound effects and music are courtesy of artlist.io. For full list, please check out the show notes. Additional material is courtesy of NASA. This episode used clips from the Artemis 2 launch in 2026 and NASA Science Live, NASA's next New Frontiers mission in 2019. The links to these clips and for more information on Titan and the Dragonfly mission will be in the show notes. This podcast is not affiliated with or endorsed by NASA. With that, be scientist. Until next time.